Hi everybody, welcome back. In this video, we are going to talk about a study that compared reporting results between multiple decision support tools for pharmacogenetic testing. And this study was done by Bousman and colleagues, which we've talked about another of their study in a previous video. And you can see here's the title of the study and the citation should you want to go look it up. So this video piggybacks off of other videos we've done where we've talked about what makes up a reliable pharmacogenetic test, which includes some sort of reporting or decision support tool. What are the consensus expert guidelines on what should be included in a decision support tool pharmacogenetic report? And we talked about how well do current panels or pharmacogenetic panels available adhere to those recommendations. So in this one, we're going to talk about how well do they match up between multiple decision support tools. So in this Bousman study, what they did is they looked at 5 patients with treatment-resistant depression. And in those 5 patients, they ran 4 pharmacogenetic panels specifically tailored towards psychiatric or psychopharmacologic treatment. And how did they pick these 4 panels? Each one must have had at least one published peer-reviewed prospective study evaluating that panel. And what did they do? They compared the results for genes that were present on at least 2 or more panels. And so in this study, this included 7 pharmacokinetic genes, which mostly were CYP-based genes such as CYP1A2 and CYP2D6, and 1 non-CYP gene, which was UDP glucuronidase transferase, or UGT2B15. It also included 7 pharmacodynamic genes, and these pharmacodynamic genes are specifically related to psychiatric treatment. So this included genes like BDNF, brain-derived neurotrophic factor, and some serotonin subreceptor genes, and so on and so forth. So what was the goal of the study? The first part was to calculate the agreement on genotyping and phenotyping results between the panels for the 5 patients they ran these panels on, and also to compare medication recommendations between those panels. So let's take a look at what Bousman and colleagues found when they compared the results in their 5 patients for these 4 panels that they ran. We're going to look at it again on genotype, phenotype, and medication recommendation. So what they found for genotype and phenotype was moderate agreement across all the decision support tools. So this ranged depending on the gene that was analyzed in the decision support tools. So for example, CYP2C19 had 100% genotype agreement across all the panels, while CYP2D6 only had 37% agreement. Similarly, it depended on the gene for phenotype calls as well. For example, CYP2B6 had 100% phenotype call agreement across all the panels, while SLC6A4, a pharmacodynamic gene, only had 20% phenotype call agreement. Now what about medication recommendation sections for these decision support tools? Overall, Bousman and colleagues found poor to moderate agreement across all medication classes included in these decision support tools. So again, this is a psychiatric-based pharmacogenetic decision support tool, so this includes things like antipsychotics, antidepressants, mood stabilizers. Across all of them was about 59% agreement. The medication class with the highest agreement was mood stabilizers with 84% agreement, while the other 3 groups, which included antidepressants, antipsychotics, and anxiolytics, had around 55% agreement. So what's up with these discrepancies? Well, for for genotype, it definitely depends on what variants were selected to be analyzed for a given pharmacogenetic panel. So for example, CYP2C19 really doesn't have many variants that can be analyzed, so it was likely, and it actually occurred in the study, that there'll be high agreement across different commercial pharmacogenetic tests. While CYP2D6 is highly polymorphic, so there's a lot more variants that can be selected by each company. And so due to that variance in the selection of the variants that are going to be analyzed by a given pharmacogenetic test, this leads to less agreement across the genotypes. Choice is a big thing here, and this choice also can influence the phenotype's calls or the translation. So for example, 2B6 doesn't have as many variants, so the phenotype calls are going to be highly concordant across the panels, but SLC6A4, and this is what happened in this specific study reported by Bousman and colleagues, one of the companies, at least one of the companies, included an additional SNP or variant in their calls for long or short allele of SLC6A4 or the serotonin transporter. And so that additional SNP led to a high discrepancy in the phenotype calls for these DSTs. Finally, what about medication recommendations? How come it's so different between the decision support tools? And partly, we don't know, because of the proprietary nature of these commercial panels. But another reason could be the source of information that's used to make medication recommendations. So an example of this might be something like we see with paroxetine. In the FDA label, it says if someone's a poor metabolizer, they might have significantly higher paroxetine concentrations. However, there's really no clinical effect, at least in the literature thus far, to actually make a medication recommendation on there. So a company could use this FDA label to cautiously say that there may be higher levels of this drug in a patient, while another company may not use the FDA label, but maybe use CPIC guidelines to say that maybe a patient may have higher levels, but there's no data to suggest a clinical risk. So let's take a look at an example of where the differences in decision support tools might arise. So this first one we're going to look at is in variant selection. So let's say we have a patient with depression and the doctor wants to start an SSRI and perform CYP2D6 testing. And this doctor can choose between two companies, a company that sells their 2D6 test in both the US and China, and a company B that sells the test in the US only. So let's compare these tests. The company A test tests for CYP2D6 star 1, 2, 4, 5, 10, 41, and the duplication of CYP2D6. Well, company B only tests for star 1, 2, 4, 41, and duplications in the CYP2D6 gene. So let's say we have two patients, one of Caucasian ancestry and one of Asian ancestry. And we know that this patient A, the Caucasian patient, is a carrier for the duplication, meaning that they have a duplication in CYP2D6, which means they're a rapid or ultra-rapid metabolizer of CYP2D6, while patient B with the Asian ancestry is a carrier for star 10. So what would happen if these patients were ran on these different companies' tests? Well, for company A, patient A would be categorized as an ultra-rapid, and that would be correct. Patient B would be categorized as a poor metabolizer, and that would be correct too. And that's because the variants included here test for a duplication, which is relevant to patient A, and the star 10, which is relevant to patient B. Now let's see what happens with company B's test. For company B's test, patient A is again categorized as an ultra-rapid because they test for duplication, so this is correct. While for patient B, they would actually be categorized based on this company's test as an extensive or normal metabolizer because they don't test for star 10. And so this would not be correct. It would actually be called a false negative. And so this is an example of knowing what makes up a company's tests in relation to your patient's ancestry, because different populations can have different frequencies of different variants or alleles within a given gene. So it's really good to know this, to have that background so you can choose the most applicable test to your specific patient. Now, let's look at one example that shows how discrepancies can arise between decision support tools based on the source of information being used. So in this example, a patient with bipolar disorder, and the doctor wants to add carbamazepine and perform HLA pharmacogenetic testing. And we have two companies we can order the tests from, Company A and Company B. With Company A, they test for star 1502, HLA-B star 1502, while Company B, they test for HLA-B 1502 and HLA-A 3101. And so why do these companies have different testing strategies for the HLA gene? Well, Company A bases their testing strategy off of the FDA label, while Company B bases their testing strategy off of recommendations from CPIC guidelines, that Clinical Pharmacogenetics Implementation Consortium guidelines, specifically for carbamazepine, that drug. So let's say we have a patient and we know that they are an HLA star 3101 carrier. So what happens if they're tested on Company A's panel? Well, this company will come back in their decision support tool and say there's no risk. Well, Company B would say there's an increased risk. Specifically, we're talking about Stevens-Johnson syndrome here, or a cutaneous reaction from carbamazepine. And so Company A would actually be considered a false negative because they didn't test for the correct variants for a given patient's population. Well, test B would be correct. So again, this shows you that the source of information used by a company to dictate what they test for can actually make a difference depending on what patient you're testing. So again, it's good to know what companies are using for their information to develop their tests, how they're interpreting them, and how they're selecting their variants that they include in their panels. I hope through this video you can understand that there's a wide variance in how decision support tools agree from company to company, and it's good to keep in mind all of these nuances as we look to use these pharmacogenetic panels in the future. Thank you for your attention.